Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today, we're diving deep into the fascinating world of reverse engineering, specifically focusing on the anti-cheat mechanisms within Call of Duty. Black Ops Cold War. Get ready for some serious technical details.
I'm all ears. This sounds intense. What's the core of this anti-cheat, and how does it differ from other Call of Duty titles?
The anti-cheat, dubbed TAC, Treyarch anti-cheat, is primarily user mode, unlike later titles which utilize Ricochet's kernel mode component. It's heavily reliant on Artadoxan, a powerful obfuscation tool, making reverse engineering a real challenge. Think layers upon layers of protection.
Artadoxan. So what specific tricks does Artadoxan employ to thwart reverse engineers?
Oh, it's a whole arsenal. Runtime executable decryption, checksum verification to detect modifications, JMP obfuscation to scatter function instructions and break IDA's flow analysis, and entry point obfuscation to hide the program's starting point. It's a nightmare for static analysis.
Wow, that's a lot. But what about the anti-cheat itself? How does TAC detect cheating attempts?
TAC uses a multi-pronged approach. It starts with basic API hook detection, checking for specific patterns in the code. It's not exhaustive, but it catches common hooking techniques. Then there's the runtime API export lookup. It hashes API names and module names, comparing them to its internal database to verify API calls.
Clever. But surely there are ways around those basic checks, right? What about more advanced techniques?
Absolutely. The author mentions debug registers as a powerful hooking method that bypasses Artadoxan's code patching. TAC counters this by checking the debug registers DR0, DR3 in each thread. It also checks for test signing mode in Windows, which is often used for driver development, flagging suspicious activity.
Interesting. So how does TAC actually shut down a process it deems suspicious?
It uses two methods, both involving inline shellcode that clears registers before terminating the process. The first uses NT terminate process, but it switches to a crash-inducing jump to 0 by 0 if NT terminate process is hooked. This makes recovery extremely difficult.
Brutal. What about external cheats? How does TAC handle those?
TAC scans for layered windows overlapping the game window, checking their size, style, and class names. It also checks for set window display affinity with WDA_exclude from capture, a common technique used by cheats to hide from screen capture tools. All this information is then encrypted and sent to the server.
That's quite sophisticated. Are there any other particularly clever techniques used in TAC?
Yes. The most impressive is probably the encrypted custom syscall stubs. Instead of directly calling system calls through standard NTDLL functions, TAC uses its own encrypted stubs. This cleverly masks the actual system calls being made, making it much harder for cheaters to monitor system call activity.
That's brilliant. It hides the syscall instructions themselves. So a cheater monitoring NT read file, for example, might miss the actual syscall if TAC is using a different function as a front.
Exactly. It's a dynamic, randomized approach that makes it very difficult to predict which system calls are being used. It's a cat-and-mouse game at its finest. The author also describes other techniques, like honeypot memory allocation to detect memory scanners, and anti-sig scanning to prevent signature-based detection. It's a comprehensive system.
This is truly impressive reverse engineering work. It highlights the constant arms race between anti-cheat developers and cheaters.
Absolutely. And this analysis only scratches the surface. The author mentions ongoing research, so we can expect even more insights into TAC's inner workings in the future. Thanks for joining us on Tech Bytes and News. Until next time, stay tuned for more exciting tech discussions.
Bye-bye.